Good afternoon. I apologize for being late. There was an important meeting I was attending. I'm so sorry. Okay, so I guess two announcements. The grades for quiz 8 will be released sometime after the class if it hasn't already. Then the deadline for lab 4 is tonight. Please don't forget to submit your peer reviews as well, even if you want to use your grace days. And the last, yes, yeah, and then quiz 9 will be released. I think after the lecture on Monday. Okay, if there are no other questions, let's continue where we were. Great. Okay, so we're talking about approximating LRU. As you remember, we talked about how expensive it is if we want to implement LRU exactly as it should be. Then we will basically need to interfere with every single access to memory by the operating system, and that would be very expensive. So we talked about the clock algorithm. Just to remind you, we had a clock hand that would go basically going over all the pages, physical pages. Every time the clock hand moves, we check the accessed bits of the page, the physical page in PTE. If it is set, then we unset it. We flush the TLB for that particular, not flushing, but just we invalidate the TLB. And then we move on until we find a page that doesn't have access bit set. Then we have found our candidate to be evicted. Okay. Now, what? So if you look at the clock hand on average, see how many moves it makes to make an eviction. If your clock hand is actually moving as slowly, then it's a good sign. It means that you're not evicting many pages. So basically, everything is fitting into your memory, and you're not needing to evict, because every time the clock hand starts moving, that basically means that you want to evict. And if the clock hand is not moving much, that means that you're not evicting. That's a good sign. What if the clock hand is moving quickly? Well, that's the opposite. It means that you're basically evicting a lot of pages. And basically, what that means is that the physical memory is not enough. It's not providing enough capacity. That's why you have to evict. Or maybe that means that your eviction policy is not a good eviction policy. So as I again mentioned, with clock algorithm, we're approximating the LRU. We're not finding the oldest page as needed by LRU. We're just finding one old page to evict. So in a sense, we're basically partitioning our pages to old and new, only having two groups. Well, can we do better? Can we, maybe partition in more than 2 groups. And that's where the idea of Nth-chance algorithm comes into play. And the idea basically is with the clock algorithm, you're giving each page 1 chance. So if your access bit is not set, that means that you're my candidate, I'm going to evict you. With the Nth-chance algorithm, we give every page n chances. So basically, the operating system keeps track of the number of times that each page has qualified for replacement. And once you hit the target, once you've lost all your chances, then it's time for you to be evicted. So the rest of it actually works very close to clock algorithm. It's just we need another variable to track how many times each page has been evicted, has been picked for eviction. So now the question is, how many chances should we give? So if you pick a large n that better approximates LRU, basically you're making more partitions. Instead of 2, you're now having n+1 partitions. Now with better approximation comes an overhead for finding the replacement candidate. As you might imagine, now your clock hand has to move a lot more, and you have to search a lot of pages to eventually find the candidate that you need. And if you pick a small n, that means that you're basically not utilizing all the opportunities that you have. Less accurate approximation of LRU, basically. What about dirty pages? So far, both with clock algorithm and Nth-chance algorithm, I only talked about access bit. Now, you could imagine situations where your candidate is a dirty page, which hasn't been accessed for a while, but it's dirty, meaning that the data inside that is modified. So if that is your candidate, then you need to write it back to the disk before you can evict it. And maybe it's better to give another chance to this one. Instead of picking it as a candidate, we can write its data back and then move on to find another candidate. That tends to speed up things. So that's what actually happens. So if you have a dirty bit and the dirty bit has the page has been picked as a candidate, then instead of evicting that page, you write its data back to the memory, basically giving it another chance, and then move on to find another candidate, because it takes time to write the data back. So next time that you come back to this page, hopefully it's not dirty anymore, and you can evict it. So now if you want to actually implement clock algorithm in your operating system, you have 2 options. One is to run your clock algorithm synchronously with page fault handler. So every time that page fault happens, you run your clock algorithm to find a page to be evicted, which is basically what I talked so far. Well, this is simple, but it kind of like you're putting clock algorithm in your critical path of finding the candidate. Another alternative is to just run the clock algorithm asynchronously in the background. So always maintain a pool of candidates that whenever you need a page, you just consult that that candidate set and pick one of them. So in essence, you're making your page fault handler fast because you always are keeping a pool of candidates. But in the background, you're adding a task that runs periodically, let's say, runs the clock algorithm to just always have this pool of candidates. And you do basically whatever we talked about. If there's a page that you want to pick and put it in your pool, you just write its data back. You don't wait for this page to be picked. So you just write its data back as your asynchronous clock algorithm runs. And if if a page is in the set in the pool and it's accessed, then you just remove it from the pool. Easy. So the pool that you have always indicates all the pages that could immediately be picked as candidates for eviction. Now, one question that we have to answer is how much physical memory should we allocate to each application? Should we set a fixed fraction of memory for each application? Should we let them all share and use as much as they need? Should we, let's say, if we find out that the memory is stressed and we don't have enough space, should we evict an entire application out of physical memory, basically pausing an application so that other applications at least run smoothly? And if so, which application should we pick? So these are questions that operating system designers have to answer. One thing that we have to know is that each process needs a minimum number of pages to run without hiccups. So one way to allocate physical memory is just to give everybody that minimum. And then if there is an extra, you can just somehow allocate that between processes, but at least give everyone the minimum that they need. And if you end up partitioning your memory between your processes, saying that process A gets, let's say, 10% of the physical memory, process 2 gets 20% and such, you need to maintain this. It's not just the first allocation that you do. You have to maintain this as you start evicting pages. So in a sense, if you end up partitioning your memory, you have to make sure that you don't evict a page from process B to bring in a page for process A. So if there is going to be any eviction for a page that has to be brought in for process A, the candidate should be from process A's current physical pages, if process A already has used its allocation. Now, what are the policies when it comes to allocating physical memory? One is equal allocation. So whatever number of pages, physical pages you have, you divide it by the number of processes that you have. That would be the allocation of each process, the allocation of memory to each process. The other way to do this is basically allocating proportionally to some weight or some some external indicator. It could be that you, for instance, in some systems, you allocate proportional to priority of each application or each process. So if you have high priority, then your allocation is higher. Somehow you need to assign numbers to priorities and then allocate based on that. Another way of weighting processes is by that minimum that I talked about in the previous slide. So if I know what is the minimum amount of memory each application needs, I can use that as an indication of weight for that process and make sure that the memory is partitioned proportionally to that weight. So if your initial need is high, then I'm going to actually give you a higher portion of memory. So you pick how you assign weights to processes. Once that is chosen and fixed, then you can just divide how many pages that you have by the sum of the weights of all processes times the weight of that particular process, which is basically here. So your allocation becomes, if SI is your weight, becomes SI times total number of physical pages divided by sum of weights. So this is basically proportional share allocation. You could also do priority-based allocations. So which is what I talked about, basically assigning those proportion and those weights based on priorities. Okay. So one of the things that happen in practice is you make an allocation and then you observe the page fault rate for each application. Maybe the allocation that you have picked is not perfect, and one process gets to have really high page fault rate and some process gets no page faults. That basically means that you have allocated more than enough to the process that doesn't have any page fault, and less than enough to the process that actually needs more memory. So somehow, if you can dynamically change the number of pages that you have allocated to your application, that could balance the page fault rate in your system. In essence, what we want is, if we give more capacity to an application, we want its page fault rate to go down, which is something that we talked about when we were talking about the anomaly that we talked about, first come first serve policy. If you have an acceptable policy, you want to, if you observe that some process has high page fault rate, what you can do is to allocate more memory to that process and bring its page fault rate down. Now the question is, how much memory should I allocate to my application? Basically, how much memory does my application need? So far, I've just said how much memory you allocate, how much memory your application needs. But how do I really know? How do I really identify how much memory my application needs? So before answering that question, I want to introduce a notion that will help us identify the memory need of each application, and that notion is thrashing. So if you have a system with, let's just assume that we have one processor in our system. If you just run one process in your system, your processor is not going to be that much utilized because your application is going to run for a bit. It's going to have an I/O, let's say. It's going to go do I/O. So when it's doing I/O, your CPU is idle. And then it comes back. It might have some, memory instructions. And when it's doing memory instructions, again, your CPU is idle. So what happens is that with just one application running in your system, your CPU utilization is very close to zero. It does some work and then it has to rest to wait for I/O, memory, whatever you name it. Now you start running more and more applications. Your CPU utilization goes up and up and up. You might think that, okay, I can just keep adding more programs, more processes, and expect my CPU utilization to go up and up and up. What happens is that at some point it will actually crash. So it goes up, 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 and then at some point you're getting marginal returns, and then at some point it actually goes down. So what happens at this point here, so in this graph on the x-axis, I have the degree of multi-programming, basically, in a sense, how many processes are running concurrently. And on the y-axis, I have the CPU utilization. And as I said, as the number of processes running increases, the CPU utilization goes up. But at some point, this is where processes start interfering in each other, in each other's execution. So one example is when you basically hit the memory capacity that you have in your system. Now, the minimum amount of memory that each process needs, the sum of it becomes more than what you have to offer. So this basically means that one or two or many of processes now have less memory than what they need. And that basically means that you have to do paging, copying one page to the disk and then bringing another page back from disk to memory. And when you start doing paging, you end up again making your CPU underutilized. And that's basically what you see here. So this is where the CPU utilization again goes down. When thrashing starts, it means that you're basically swapping pages back and forth between the disk and memory. How do we detect thrashing, and what's the best response to thrashing? Now let's start about going back to how much memory basically my process needs. If I know that will help me in understanding thrashing and having a better policy to deal with thrashing. So what you see here in this figure, it's on the x-axis. I have the execution time. So as this whole thing is for one process. So on the x-axis, I have time and execution time, and on the y-axis, I have the memory address space. Each time my process makes a memory access, I put a dot here. So I say at this time, my process accessed this page number inside its address space. So, and then I get this dot plot here. Now, what does this say about my program? With this plot, I can actually detect working sets of my process. What is a working set? Working set is basically a set of pages that are referenced by the process in a sampling window. So set a sampling window and look at all the pages that your application has accessed. The size of those become your working set, the size of your working set. If you don't have enough memory, if you haven't allocated enough memory to your process, then your process starts thrashing, causing it to do paging, going back and forth between memory and the disk. Now, usually you have structures like this. So if I'm just putting marks on this graph, as you can, for instance, see, now I can just run my sampling window on any particular window. I can look at all these, areas. There are here also. I didn't mark them, all of them. I just marked some obvious ones. And then I can easily detect the size of my working set. It's basically what the area, the number of pages I have in this window that I'm accessing. That would be my working set in this window. If I plot the heat rate, or it could basically here be a page fault, sorry, the opposite of page fault, 1 minus page fault, 1 minus page fault rate, which would be heat rate, number of times that I heat in memory, as a function of the allocated memory to my process. So fix a window time. Let's say we're just interested in this window, and we can run the application many times. And each time I'm going to allocate a different memory capacity to my application and measure its heat rate in that window. What you will observe is that your heat rate as a function of memory allocation will be something like this, a step function like this. And what happens here is that you get bumps here in your heat rate when you fit in one of these areas that I have marked here. So once the memory capacity is enough to hold in this area, once I have all of this area, I get a bump in my heat rate. It just increases as a step function, because now I don't need to do paging for that area. I have enough capacity to hold it. And as you can see, as you increase the memory allocation, you get more and more of these steps until it gets basically flat. There are not much more pages to fit in. And that would basically tell you the size of your working set. So whenever this flattens out, you can go to your allocation, and that tells you what is the working set, what is the size of the working set of your application at this time interval. If you are implementing a memory allocator, you could track the working set size of your applications as you go. Basically, what you do is you keep track of pages that are referenced by your application at any given time for a window in the past. So if you're here at time t1 and the window size is delta, then your working set at time t1 for this window is 1, 2, 5, 6, and 7. So these are the pages that you have accessed, t1 minus delta to t1. And at t2, as you can see, the working set changes, right? Because the pattern that your memory access pattern changes. As your memory access pattern changes, your working set size also changes. So basically, you can maintain this sampling window it could be either as like time based, or it could be instruction based. So if you go with it's roughly equal. So if you do time and instruction there, it's an approximation, but you could just, you know, keep track of all the pages accessed within the last 1,000, let's say, or 1 million or 10 million or whatever you choose instructions ago. If you pick this window very small, then you're basically not gathering enough information about the locality of your pages. If you have delta very large, if delta is too large, then you're basically memorizing something from the past that might have changed. So your data wouldn't be that up to date. So if you basically choose delta to be infinity, it means that from the beginning of your execution, your working set basically becomes probably the entire virtual addresses space. And as you can see, that's pretty much like there is no value in that, because you sort of know that you're going to access certain pages. What you care about is, in a particular window of time, what are the pages that I need. And what you can see is, if D is the size of your working set, then if your memory allocation is less than your working set size, then you start thrashing. So this is one way of, first of all, tracking how much memory each application needs, a notion to realize that thrashing is happening, and a notion to use, if I know the working set of my application, I can use it as a weight, for instance. I can use it to adjust memory allocation. I can do a lot of things with it. And this is basically telling you how to do it. Okay, so another thing that could cause page fault is compulsory misses. Basically, the first time you access a page, because that page is not in your memory, that is basically a compulsory miss. You have to go out and grab it. One way to deal with compulsory misses is to do prefetching. So if you access a certain page, maybe you should bring in all the other pages close to that page. So the notion of clustering is basically what I just described. When you have a page fault, you bring in all the pages around one page. This is a little bit tricky, how many pages you want to bring in, but in essence, you want to take the opportunity to bring more pages because of the way that we'll talk about how these pages are written in the disk. Usually it's the case that sequential pages are written in your disk sequentially. Usually it's not always the case, but sometimes it is the case. And if that's the case, certain types of storage devices have better performance if you read sequential data from them rather than random data. One example of such a storage is those old magnetic hard disks. So for those, if you already are accessing your page and you're already reading data from that position in your disk, it's very low cost to read the next page or the previous page before this page that you need. So you can bring those pages with a little to no overhead, so you can actually use that. Okay, I think this is the last topic I'm gonna, I believe, cover, and that is core map. Excuse me. So far I have talked about everything we've seen so far has been, I have a virtual address, I want to find physical address. So it's just one way from the virtual address to physical address. Now, usually you actually want to know the inverse as well from your physical pages to your virtual pages. And that is important because you have these situations where a physical page is mapped to multiple virtual pages. And it could be actually that these multiple virtual pages are in different processes. So you want to know if you're evicting a page, which processes would be affected by this. So usually it's the case that the operating systems have to have an efficient way of figuring this out as fast as possible to know exactly which pages are assigned to which processes. Because if you are evicting a page, you have to go and invalidate page table entries, and you basically need to know which processes are affected by this eviction to go and update all those processes page table entries. So that's very important. Yeah, there are many ways to do this. Different operating systems do it differently. But what is the most important thing is that you definitely need to have an efficient data structure to keep track of what physical pages are actually allocated to what virtual pages and in which PTEs. And that's basically the bottom line. Okay. Now let's move on to next lecture. Okay. So in this lecture, we're going to talk about I/O subsystem and storage devices. This is the outline. We'll talk about an overview of the I/O subsystem. I'm going to spend some time talking about I/O performance. Whatever we talk here, we're going to talk about some queuing theory. It's applicable in other systems, maybe in networks. Maybe you can go back and apply it to CPU scheduling. It's very general. We're going to focus on its application in I/O system, but what you learn here is applicable in many systems, in distributed systems, in networking, in CPU scheduling. It has implications in many systems. So I'm going to spend some time on the I/O performance. Again, it's in the context of I/O, but whatever we talk about has general implications in other systems as well. And then eventually we're going to talk about storage devices. as a particular example of I/O devices. And in particular, we're going to talk about magnetic storage and flash memory. Okay, so far, what have we learned? We have learned how to manage CPU and memory. That's basically pretty much what we've seen so far. Next, we're going to actually focus on I/O. Without I/O, computers are basically useless. It's kind of like a, you know, if you have brains without bodies. I/O is how computers interact with outside world. Now there is a variety of I/O devices that could be connected to your computer. You could have accelerators like GPUs, TPUs, FPGAs that are connected to your system. You can have storage devices. Again, you have variety of different storage devices that could be connected to your system. You can have transmission devices like your wireless adapter, your network adapter. You could have human interfaces like a keyboard, a mouse, or you name it, right? So there is a variety of I/O devices that could be connected to your system. Now, the question that an operating system designer has to answer is that, do I want to deal with all of these different types of devices differently, or do I want to, as always, introduce an interface and a standardized interface, and then make all the devices implement that interface and operating system optimize everything around that interface? And that's basically what has happened throughout time. You still have to deal with that diversity, but you can actually, in a modular way, push that to the device driver and factor it away from your applications. So you can provide a uniform API to your applications through the system call interface. And under the hood, you can actually implement all those different varieties of different devices, either the operating system itself or within the device driver coming from third party, but then communicate with those devices. Now, the other thing about I/O devices is that they're coming from everywhere. Anybody can, design and manufacture their I/O devices. The operating system should not rely on the device being, doing what it's supposed to do all the time. So we have to consider the fact that these devices could be unreliable. Now the question is, can we use those unreliable devices but still be reliable to provide reliability to the end user, and basically mask any fault or failure from the end user and the applications? Don't let a faulty device to crash the entire system. The other thing about it is that we have to deal with is the fact that these devices have different speeds and different performances. And again, that also is introducing challenging issues to operating system designer. Some of these devices are extremely fast. Some of these devices are extremely slow. You have different, latency and responsiveness requirements that you have to stick to. And we'll talk about this in a little bit more details in this lecture. So as an example, just to show you something about the last point that I made, here in this graph you have different devices on the x-axis. So this is a bar chart. On the y-axis, I have gigabyte per second. So you can just look at this graph and notice that you have basically orders of magnitude difference in a speed of different devices. So almost 7 orders of magnitude difference you can see in this graph. Your system better be able to handle all these this wide range of speeds, and better provide what the end user needs in terms of latency, dealing with all these variable speed devices. The goal of your I/O subsystem has to be providing a unified interface that could be used by the applications. You basically, if you're familiar with the Unix system, if you write a code like this where you open something in your dev folder, and you start, printing in it or reading from it, it usually works, no matter what this something is. So it could be your keyboard, it could be your any other devices that you have on your system. From the program's point of view, they're all dealt with through the system call interface that the operating system provides. So we'll talk more about this interface, but in a sense, we're dealing with treating them all as files. And we're letting the operating system and the device drivers to deal with the details of how this interface is translated to the language that device understands. The goal of this lecture will be to tell you different ways that operating systems manage devices. So basically, we'll learn how to communicate with controllers that most of these devices have. How do we transfer data between the device and the program, and how do we manage the devices, and a little bit about modeling the performance of our devices. Okay, I'm actually going to give you 2 minutes of break, and then we'll continue. Okay, we're back. So let's talk about devices. Let's start from operational parameters of our devices. The first thing that we have to consider is data granularity. What is the granularity of the data that is being communicated back and forth between the device and the programs? It's usually bytes versus blocks. The other thing that we have to consider is access pattern. Do our devices support sequential accesses only, or can I have random accesses to different parts of the memory of the device? The other thing is the notification mechanism that the device uses. Should the CPU poll on the device, or does the device support interrupts? The other aspect we have to look into is the data access. How do we access data for our device? Usually, if you have a character or byte device, then you can access data 1 byte or 1 character at a time. Normal commands for this are get and put. And you usually want to, layer things up with your libraries and maybe provide more utility functions to your applications, like reading a line or editing a line instead of just characters. For block devices, you can read a block of data or write a block of data. Normal commands for these devices are open, read, write, and seek, depending on the type of the device that you have. And then the third category that is different from the two that we mentioned is the networking devices, like your Ethernet, wireless, or Bluetooth. Usually, you have separate set of system calls to interact with these devices. I think you've worked with sockets, the socket interface in ECE 252, so you should be familiar with how they are different from normal files that you have had. Like you can, for instance, call select on your sockets and ports. The other aspect is timing. Your devices could provide blocking interface, or basically operating system could provide blocking interface for some devices. And that basically means every time you want to communicate with them, you have to wait for reading or writing data. The other one is non-blocking. You can just notify the device to transfer the data, and once once the data is transferred, then you get notified. Similarly, you can have asynchronous interfaces. Sorry, I think what I described with non-blocking was actually asynchronous, where I mean, both asynchronous and non-blocking are non-blocking. But you just with the asynchronous one, you give a pointer to your device where the data should go, and once the data is there, then you get an interrupt that tells you, okay, I'm done, the data is ready. With the non-blocking interface, you basically check at that moment if you have the data, you successfully read or write it, and everything is done. And if not, then you just get an error message, or your function returns. Either you yourself try again, or you just move on. So that's basically the difference. Now let's talk about notification mechanisms I alluded to. You could either do polling. This basically means that your CPU periodically checks the device, the status register of your device, to see if the data is ready. This is, you know, in one sense is good, and that sense is that you're not interrupting your CPU a lot. But the cost of it is that your CPU is basically wasting its time to just check a register and wait for the event to happen. So as a result, many devices are interrupt driven. Basically, the device will interrupt the CPU once the data is ready. The good thing is that CPU is now not wasting time, but one downside could be if these interrupts are really frequent, then you could slow down the tasks that are running, because they keep being interrupted, and then you have to run the interrupt handler all the time. You could potentially use a hybrid model that you would usually use, for instance, for the network adapters. For the first packet that is delivered, you could be notified by interrupts, but once the first packet comes, you have an indication that more packets are gonna come. So at that point, you can start polling. So you're basically using a combo of the two. A typical layout of devices in modern architectures is depicted in this figure. I have to say it's not, this covers majority of architectures, but there is not a universal way of connecting the devices to your processors. Different architectures use different models, but this is one typical way. So to talk about this, let's start from the top. So you usually have your CPU connected to the North Bridge, and the name that usually people use for this is your memory controller hub. Obviously, it's connected to your memory, this hub. And then it's also connected to maybe for instance, the graphic card, which has to have really high bandwidth connection to the memory and the CPU. So you usually connect your your GPU to the North Bridge, and then from here you have a branch that goes to another hub, Southbridge, or your I/O controller hub, where bulk of your I/O devices are basically connected to this one. As you can see, like your USB, your Ethernet, your PCIe bus, your PCI bus, and again, so takeaways. You usually have a memory hub. You usually have a I/O controller hub. The things that are not, different architectures make different decisions. Like back in then, you had the North Bridge having its own chip and being separate from the CPU. These days, most of the architectures that I know, this memory controller has been integrated into the CPU chip, so it's in the package, and that it speeds up things a lot. If they're in the same chip, the closest it is to the CPU on the same chip, the bandwidth is higher, and that really helped at some point increasing the performance of the CPUs when they integrated this memory hub. Nowadays, so it used to be that this I/O hub still was implemented outside. It was like its own chipset. But many new architectures, AMD, I think, pioneered this. They also have taken another step to integrate the I/O controller inside the CPU package as well. That increases the bandwidth dramatically, and opens new horizons if you wish. But again, so this is just a typical North and Southbridge layout that you usually see in modern computers. One element that has was introduced in the past and has now become like sort of mainstream is PCIe devices. So that's why I picked them to talk about them, because like the trend is now most of our devices. So it was the case a while ago that you had all sorts of connections on your motherboard, different types of connections. But as we're going forward, and what I'm observing myself and what you might notice is that there is sort of a conversion into providing PCIe as a standard connection for most of the I/O devices. Basically, most of the ones that I know, like you can connect your USBs through PCIe Express. You can connect your network, your NICs, your wireless, your Bluetooth, even your GPU. All of them could be connected to your processor through the PCIe Express lane or lanes. That's basically the reasoning behind why we're talking about PCIe, because it's basically very common these days, and it seems like the trend is towards this being the main way of communication. So a little bit of history on PCIe connections. You have this evolution of PCI. PCI was when we started this PCIe, and it used to be like a parallel bus, but soon they realized that parallel buses have limitations that are not, a perfect fit for connecting I/O devices. In particular, multiplexing address and data was an issue when you had many requests on the same connection bus. And I would say the main drawback of PCI when it started was that because all the devices were connected to the same bus and they were sharing the same parallel bus, the bus's speed should have been dynamically adapted to the slowest device, because whatever message you were sending on the bus, you want all the devices to be able to listen and answer to those messages that are being sent on the bus. So you have to bring the speed down to the slowest device that you have in your system. Now, that changed. We moved to PCIe, which basically what it does is that it just goes and picks the serial and packet base point-to-point architecture, very similar to how networks work. So in this new design, you have each device is connected to its own PCIe switch, which then connects your device to the bidirectional link. And now your different devices could have different, rates, and you don't need to slow down the entire bus for your device, because your device is only communicating with the PCIe switch that is connected to it, and then that PCIe switch is kind of like an interface that buffers or transfers the packets coming from your device to the bus. Very, very, very similar to packet switched networks. So now you can have different lanes, and using more lanes mean basically having higher bandwidth. So different devices, you have devices that use only one lane, you have devices that use 4 lanes, devices that use 8 lanes, and then devices that use 16. I think there is also 32 lane. It's not that common. Mostly 16 is the one that motherboards and processors support usually. One thing to note here is how Linux actually seamlessly migrated from PCI to PCIe, and that came from the fact that they really use a good abstraction when they were designing how Linux is going to deal with PCI devices. So once PCI moved and became PCIe, they kept everything and they kept the base and then they added features. So now if you have a PCI devices connected to PCIe bus, if you if you had a driver that was written for old PCI protocol or devices, you still can use that driver even with a PCIe device. The only thing is that the driver cannot use the new features that are added, but it still can communicate with the device because the interface hasn't changed. So just because I started this lecture a little bit late, I'm going to go 5 minutes over time. I really sincerely apologize. I somehow thought that today's lecture starts 1:20 instead of 1. I mean, it ends 2:20. For some reason, I thought it starts 1:20. But anyways, so I'm going to go 5 minutes over time. If you need to leave, definitely do so. The lectures will be recorded and posted online, so you can definitely watch. Okay, so here what you see is a typical architecture for PCIe. As I mentioned, you have a switch that connects your PCIe endpoint to the PCIe bus. So you could have different endpoints connected to your switch. You usually have bridges if you want to, connect other buses or other technologies to your PCIe bus. So this PCIe to PCI or PCIX endpoint or bridge acts as an interface. So it will know how to communicate with the devices on PCI or PCIX, and then it just converts those packets to what is understandable on the PCIe port. For this particular example, I'm connecting this figure has connected memory to this root complex. So the root complex basically is the main bus that connects the CPU and memory. and all these devices are basically connected to it. Now, when you connect your device to become an endpoint, a PCIe endpoint, what you usually have on your device is a device controller. It's a if I were to show you, like in this device that I have, I think it's a NIC card. This is basically the heart of the device, which is a controller. Now, this controller has different parts. The part that is of interest to the operating system is basically how to communicate with it. So usually what you have in your controller is a set of registers and bunch of buffers that you have on the device. And so some examples of the registers you could basically have, you know, a command register, a status register. We'll talk about base address registers. So these are registers that you can read or write depending on their functionality. So the operating system can communicate with the device driver using these registers. The other you know, interface for communication is those buffers. So if let's say the device wants to send some data, it could put them in its buffer, and then somehow operating system can come and read that data. Or if the operating system wants to, you know, send a series of commands to the device, it could use those buffers to communicate. So this would become like a device-dependent sort of thing that would be managed through the device drivers. So here I think I have the example of a typical PCI device. During the initialization, the operating system or the BIOS start reading these status. It's usually called the configuration space registers that would be used to automatically configure your device, again, when the operating system is booted or when the BIOS is starts running. One of these registers that I have both in the figure and here in the slide is the base address register. It basically tells initially when you turn on your system, what you can read from the base register is how much memory this device is asking from the operating system to allocate to this device, how much memory it needs in the physical memory. And then once operating system allocates that memory to this device, it then writes to this register the base address of the region of physical memory that is allocated to this device. Hopefully that makes sense. So initially you read from it to see how much memory this device needs. And once you allocate, you just write to it to tell the device that this is the region that is now allocated to you if you want to use it. Now, the way the operating system is going to, I'm sorry, I think I'm almost done. This is going to be the last slide. So the way that the operating system is going to use these registers and these buffers will depend. So there are two ways to do this. One is port mapped I/O, and the other one is the memory mapped I/O. So with port map I/O, we're going to actually have the devices having their own separate address space that is separate from the physical memory. So how can we accomplish this? Well, what we can do is to have a separate bus for our I/O devices. And then every time the CPU wants to communicate with I/O devices, it uses a certain set of addresses and then communicates through the I/O bus. So it's completely isolated from memory. And to do that, usually you have to have instructions that are specific for I/O. So in Intel, for instance, you use in and out instructions. If you have Intel microprocessors that have separate bus for I/O devices. So for instance, you say out address 21 to AL. Sorry, AL to address 21. This basically means write whatever you have in AL in the lower bits of register A to this address. But because you're using out instead of store, you're using out, the hardware knows that it has to use the I/O bus instead of memory bus. So if instead of out I had store, then the CPU would use the memory bus instead of I/O bus. With memory mapped I/O, however, you only have one address bus and one address space for both physical memory and your I/O devices. As a result, they both have to share the address space. So what happens is that operating system, keeps a region or allocates a region of address to I/O devices. But then you can basically use your load and store instructions to communicate with both memory and I/O. Now, your I/O devices are connected to the same bus that your memory is connected to, so they can just realize that the CPU is talking to them if they know what range is allocated to them. So they will just listen to the commands and instructions that are using the addresses that are assigned to those devices. Okay, so again, for the third time, I apologize for being late. Sorry, I went over time and I started late. We'll talk to you on, I think, Monday, yes. So thank you for everyone who attended the lecture. Have a great weekend and talk to you on Monday. Take care, be safe, bye-bye.